Okay, so, generally speaking, the test one went well. Quick explanation about how the scoring is. The graduate students had to do all seven problems. So I thought, well, okay, I'll make the 15 points each. This has to 105. Man, it's noisy out there. Okay. Which happens to 105. But then I would take that really, everything's out of 100, so perfect score would be 105%. That's for graduate students. I thought, well, I'll have the same top line number for the undergraduates too. So that's why, so for instance, if you saw that you lost, say 6 points, then your score's 99. So, just because I started talking from that point. But you can still think of it as being out of 100, so you can have a little more than 100%. All right. Okay. And I also want to make clear for we'll have one more test later on plus the final. So for those, and I should have made this clear previously, that for undergraduates, since there's going to be a situation where you don't have to do every single problem, but if you choose to do every single problem, then I can include them as bonus. Okay. So you should be able to see in Canvas, for each student, I left a comment, just like I do in homework, indicating where points were lost. So if you have any questions about that, you can just let me know later. All right. So we've spent a lot of time on the heat equations, the UT equals coefficient UXX, parabolic equation. So now we're going to move on to the next type of PDE, or second order PDE. That is a hyperbolic equation, namely the wave equation in one dimension. So the content that I'm covering today comes from 2 short lessons. Let's do it all at once. Okay, so first, I'll talk a little bit about how the wave equation is derived. We saw the derivation of the heat equation. Similar ideas are in play for deriving the wave equation, where you're taking the physical laws, just different ones, and translating them into PDEs. So what we have here is we're modeling a vibrating string. So the solution, u of xt, is the displacement of a string at the point x at a time t. So you have some finite length string between those tied couple endpoints, depending on your boundary conditions. And so what Newton's second law gives us is this: as you know, that the second derivative with respect to time, that gives you acceleration. And we have, we're looking at a segment of a string. We have the length of a segment, which is delta x, and then we have the density, rho. So that's, here we have a mass equals density times volume thing going here. So here we have mass times acceleration on this side, and by Newton's second law, that is equal to force. So everything on the right side accounts for the various forces acting on the string. So we have, this is our most essential term, is the tension, and then if there is an external force acting on the string, we include that here. And then we have a frictional force and then a restoring force. Now, most of the time we won't have these extra terms, but that's when I mentioned them, so you can see how they're accounted for in the PDE. But the force of main interest to us is the one due to the tension. So what we have here, this is the tension on the segment. So what's happening, the tension at the endpoints, and I'll show you a picture. This is actually taken from the text. So here's our segment of the string, starting at x and going into x plus delta x. And the force due to the tension comes from the angle that the string makes with the x-axis. So this angle theta 1 here and theta 2 here. And so if you consider right triangle trigonometry, that so if I'll make it a little bigger. So at this point where you have the angle theta 2, that sine of theta 2 would be equal to the length of its opposite side, which is a change in u value, and then the sine is opposite over hypotenuse. But when the angle is small, delta x is small, then there's not much difference between the length of the hypotenuse and the length of this adjacent side here, which would be, so what happens in this case is it's reasonable to approximate the sine of this angle by change in u divided by change in x. So this leads to approximation of a tension force by the constant t representing the tension and the derivative of u with respect to x. Okay. Now, so we do that for the tension at both ends, at opposite sides, which are dealing with opposite ends of the segment. Then we have this difference of du dx values. And that's what leads to this term right here. So now what we can do is take this equation, divide through by delta x. And in these terms, the delta x's will just cancel. But with this divided by delta x, and then we let delta x go to 0, what we have is a definition of derivative. And it's going to be the derivative of ux, which leads us to uxx. So this is the PDE right here that comes from letting delta x go to 0. Now, we're also dividing through by rho, so we get utt by itself. So we're going to have a coefficient here, t divided by rho. And that becomes the coefficient alpha squared of uxx. And then we just rename we redefine these, take into account the fact that we're dividing by the density rho. So this equation, called a telephone or telegraph equation, most of the time see it as a telegraph equation, describes what's called transverse vibration of a string. So we have a vertical displacement, positive or negative, over time. That's what's being described by this equation. So, unlike the heat equation, the time derivative here is second order. When you have an equation that's a second order derivative in time, that means you must have two initial conditions. You have to specify the initial displacement, u of x0, and now we have this initial condition also on du dt at x0. So you have to describe the initial position of a string at each point x and the initial velocity of a string. This whole derivation is assumed that the density rho is a constant. If the density depends on x, so the string is not homogeneous material, then the coefficient, alpha squared, is going to depend on x now. And that leads to, instead of having alpha squared uxx, you're going to have alpha squared ux, derivative of the whole thing with respect to x, instead of this. So it's kind of like with the heat equation. You had a homework problem on this. If the coefficient k depends on x, then it gets lumped into the outer differentiation. And the reason for that is that at the two endpoints of the segment, the different densities would apply. Okay. So as far as how we can interpret the wave equation, if we ignore these terms here, we have utt is alpha squared uxx, that the acceleration is proportional to the tension. And that tension is described by uxx, which is a concavity of the string. So if the string is concave up, so for instance, suppose the string is pulled down, then you're going to have a positive acceleration. And the greater extent to which the string is pulled down, the more higher the acceleration is going to be. Whereas if a string is pulled up, which would give it a concave down shape, then there's going to be greater acceleration downward. And that's what leads to this vibration. So there are questions about where the wave equation, the telegraph equation, comes from. Here's some other uses of the one-dimensional wave equation. So you can model other situations. So it can describe model sound waves or longitudinal or torsional vibration of a rod. So the meaning of the coefficient alpha squared is called Young's modulus, which measures elasticity. Also, electric current along a wire. So now we have the transmission line equations. So a lot of cases where you have PDEs that all have a similar appearance in terms of what derivatives they have, that have very different physical interpretations and therefore applications. Just because of the kinds of physical laws that are in play to derive each one. Now, what we want to know, once we have a wave equation, is how we solve it. And so we actually have a solution formula that's, in terms of the initial data, that's fairly easy to work with. And more so than the heat equation. Because the heat equation, we also saw a solution formula that involved a convolution of the initial data with a Gaussian function. But then that solution would be left in all integral form. But here, the formula that we get here is a little easier to work with. So we're going to consider the Cauchy problem for a wave equation. So UTT is c squared uxx, where c is going to turn out to be the speed of the wave. This is a Cauchy problem. It's defining the entire real number line, no boundary conditions. And then here are two initial conditions. So u of x0 equals f. The udt at x0 is some given function g of x. And what I'm going to do is show you how to get the solution formula, which is called D'Alembert's solution. And I'll show you two different ways which can be derived, one on this first Cauchy problem, and also one on a bounded interval using separation of variables. All right, so first we'll just deal with this Cauchy problem. So what we do is we define new variables that take into account wave propagation. So here we have x plus ct, and I'll call that c, and then x minus ct, call that eta. So what we want to do is rewrite this PDE to involve derivatives with respect to c and eta. Now, in order to do that, we have to figure out the derivatives, how to write derivatives with respect to t and x in terms of xc and eta. So that means using the chain rule quite a bit. So as an example, here's du dx. So by the chain rule, so we have du dxc, dxc dx. So you can think in terms of, here we have, for this derivative, we have dxc on the bottom. For this derivative, we have dxc on the top, effectively canceling. And then similarly over here, we have du d eta dx. So now we have derivatives of u with respect to our new variables appearing here. All we have to do is fill in the derivatives of our new variables with respect to our old. And for that, we can just turn to these formulas here. Because, so I can take a derivative of this with respect to x or t, in this case x. So dxc dx is going to be 1, and the eta dx is also 1. So du dx is just uc plus u eta. Now, for the second derivative, we're going to use this first derivative we have here, because the derivative of anything with respect to x would be its derivative with respect to xc plus its derivative with respect to eta. So that's what I'm doing here. I'm thinking of this as, I'll just write in here, uxx. And then, so what we have is the differentiation operator with respect to x is the same as the sum of these two differentiation operators with respect to xc and eta. So that's what's happening here. That ddx is now being expressed in terms of the new variables. And that's why I get this second step here. But now, I can use my previous formula for ux and just substitute that in here, where you see ux. So now, everything is differentiation in respect to the new variables, and then I can just work out what that is. And here's my formula for second derivative with respect to x, in terms of all possible second partial derivatives of u with respect to c and eta. I can do the same with ut. If you look at how I've written du dt here, it's the same thing as what I did here to get u dx, except now the derivatives of the new variables are with respect to t instead of x down here. So that means I have to take the derivatives, I go back up here, take a derivative of c and eta with respect to t now. So I'll get so derivative of c with respect to t will be plus c, and derivative of eta with respect to t will be minus c. So that's what we end up with down here. And I use the same idea as with uxx to express utt in terms of the new variables. So now suppose we keep in mind that our PDE is UTT equals c squared UXX. Well, let's take a look at UTT and UXX as we have them written here. Here's UTT. Notice every term has a c squared in it. And now, if I were to take this UXX and multiply it by c squared, they're almost identical. The only difference between them is that here we have plus, it would be plus 2c squared UXC eta. Here I have minus 2c squared UXC eta. So if I set UTT and c squared UXX equal to each other, almost everything is going to cancel. The only thing left would be the term involving UXC eta. So now we have this much simpler PDE in the new variables. Anyone tell me where we've seen this PDE before?
Was this in the first homework?
Yes, it was one of the problems from lesson 1, where you had to come up with a general solution to this PDE. And it's actually why that problem was introduced, because it's going to come up later. So yeah, you know how to solve this from that homework problem, that the general solution is some function of eta plus some function of c. So we know that our solution in the new variables is going to have this form. But now we have two questions to answer. One, what will the functions be? And then how do we obtain u of xt? Because we want to have our solution expressed in as a function of our original variables. All right. So the only part of the problem we have not yet taken into account are the initial conditions. So we have two constraints, u of x0 is f of x, ut of x0 is g of x, those two initial conditions. And we also have these two degrees of freedom, that these unknown functions, phi and psi. So we use those. So we're going to have a situation of two equations and two unknowns. Let's figure out what those equations should be. Okay. Now, one of our initial conditions is on du dt. So we need to figure out what our solution, our general solution is, what its time derivative is. So here, if I take this formula, so then I want to take the derivative of this with respect to t. So that's going to be phi prime of eta d eta dt, and then plus psi prime of xc, derivative of c with respect to t. And from before, I know what those derivatives are. That eta is x minus ct, so its derivative with respect to t is minus c. And xc is x plus ct, so its derivative with respect to t is plus c. So now suppose I evaluate this equation at t equals 0. Well, eta and xc are x plus or minus ct. So if I plug in t equals 0, eta and xc are both equal to x. So that's what I have down here. So now I have ut of x0, which is this, is equal to g of x. Then I have the other initial condition, u of x0, so I also plug t equals 0 into my general solution. So now I have phi plus psi is equal to f of x. Now, what I'd like to have, I have two linear equations. I'd like to have two linear equations and two unknowns. However, I do not have that right now because this equation involves phi and psi, and this equation involves their derivatives. So, no problem. What I can do is take the integral of both sides of this equation. And that gives me this. So here we just take the primes away on the left side, and then we'll have some antiderivative of g. And for convenience, I've decided to describe this as we're writing as a definite integral where x is the upper limit. So it's still an antiderivative. The lower limit is some x naught. Fortunately, it'll turn out later that the value of x naught is irrelevant. I'm going to get it to cancel out later. Because, of course, as we know, the antiderivative is not unique. But I'm just on an arbitrary antiderivative here. So now I can take this equation with the first equation up here, and I have this system of linear equations, two linear equations in two unknowns, phi and psi. And I know how to solve that. All right. Okay, we can also solve two linear equations and two unknowns, but the idea is to have a formula for the solution. And to get that formula, I'm writing the system in matrix vector form. So the left side here is equivalent to this matrix times this vector, phi and psi, my unknowns, equals this vector of right-hand side values over here. And that makes it easier for me to come up with a solution formula because what I have is phi and psi, this vector is equal to the inverse of this matrix times this vector. Here I have a formula for the inverse of 2 by 2 matrix. It seems to come up in so many different situations. It's one of those things that a math student ought to have memorized. So now, I can say phi and psi is, this is the inverse, or this is the inverse of this matrix, those are right-hand side values. The actual inverse is worked out here, because the determinant of this matrix is 2c. So I have to divide everything by that. So now what I can do is carry out this matrix vector multiplication. And what I do, so 1/2 times f minus 1 over 2c times the integral is the first element phi. And then 1/2 times f plus 1 over 2c times the integral, that's the second element, psi. And that's what I have written out here. So this is my solution. So now I know what phi and psi are. So now I can put together a whole solution. So here's my general solution from before, phi of x minus ct plus psi of x plus ct. So now I'll fill in what those are. So I've just dumped those in here. Where we see x, I fill in x minus ct. That gives me these two terms. And then here, wherever we see x, replace it with x plus ct, and that gives me these two terms. So now I'd like to, so now I just group everything together. So I'll take up terms involving f, put them together. And here I have integral, okay, I should mention for phi, I have 1/2 times f minus 1 over 2c times the integral. But what I've done with the integral here is I flip the limits, so I have x on the bottom and x on the top, which changes the sign of the integral. Therefore, this minus becomes a plus. So I need to mention that I did that. Because now if I look at the two integrals, I'm integrating from x minus ct to x naught, integrating g, plus integral from x naught to x plus ct. The integrands are exactly the same. So when I can chain these two integrals together, going from x minus ct to x plus ct. So this is what I meant earlier about the value of x naught not mattering. It ends up being canceled out. So this is what we get from combining those two integrals, and we're done. So this right here, this last line, is D-Limbert's solution formula. So this is a solution of a Cauchy problem for a wave equation. In terms of the initial data for f and for g. Questions about this derivation? I guess it's an illustration of the saying that mathematics is the art of reducing all problems to linear algebra. If we ignore the g term, let's suppose that g is 0. Here we have transformation, the graph transformation of x. So this is, the graph of x plus ct is a graph of f shifted to the left by ct units. Here, this is a graph of f shifted to the right by ct units. So what happens is, whatever initial data you have, half of it gets sent shifting to the left, the other half shifting to the right, and this constant c indicates the speed at which the shift is taking place. So we have two-way propagation from this solution. So suppose f is 0, except on a small interval. Then, like, suppose your initial data is just a lump sitting on the real number line. Half the lump's going to go to the left, half the lump's going to go to the right. And it doesn't change shape either. It just goes in that direction. Okay, so that's one way to see the solution formula. But another approach, I'm going to focus on not a Cauchy problem, but a wave equation on a finite interval. So I can show you what happens with separation of variables. And it's going to be similar to separation of variables that you've seen, except now we have a second order time derivative to deal with. So your time ODE is second order instead of first order. So first order, heat equation, you got exponentials. Now we'll have sines and cosines for t as well as x. Okay, so here's our problem. And we'll have type 1 or Dirichlet boundary conditions. U is equal to 0 at the endpoints. Same initial conditions. So what happens with separation of variables this time? Same ODE for x. Very similar looking ODE to the x1 for time. We just have this extra coefficient of c squared here to go lambda squared. So solving one for x is no different than what you were doing before with the heat equation. The spatial ODE is the same. So, and from prior examples, we know what that solution is in this case. And we're going to get a Fourier sine series, sine n pi x over L. So really what's happening is the value of lambda is this coefficient of x here, n pi over L. So, and you can see from the appearances of the two ODEs, they're going to be exactly the same except for this extra factor of c squared here in the time one. Your general solution for the time equation, the time ODE, we're going to have this linear combination of cosine and sine. So, whereas before we had, and lambda, as mentioned, is n pi over L. So, in the time ODE, lambda is multiplied by c. So, whereas in the x ODE, you had n pi over L times x. Here we're going to have n pi c over L times x. Also, we don't yet know about which combination of sine and cosine because in the x ODE, where we have sine or cosine is dictated by the boundary conditions. For time ODE, what combination of sine and cosine you have is dictated by the initial conditions. So when I look at, so what I'm doing here is, I need to fill in more steps than what I have written out here. So I'll go ahead and do that as I go. So u of xt will be equal to a sum, 1 to infinity, of Tn of t, xn of x. So all I've done here to go from here to here is that I've just replaced Tn of t and xn of x by these solutions, and that's how we got here. Then what I do is, here I have a cosine times a sine. I can use what's called a product to sum identity, so trigonometric identity. So this product, this sine times this, cosine times this sine, gives me this sum of sines down here, all of that multiplied by an. And here I have this product of sines that can be written by the same kind of identity as a difference of cosines. And I also have this minus up front that got introduced by that trig identity. And all of this is times 1/2. So the 1/2 comes from these products of some identities. I just went ahead and factored that out. And because what happens with these trig identities is we end up adding the arguments of sine and cosine together, or subtracting them. That's how we get x plus ct, x minus ct, that you would recognize from the previous derivation. Any questions up to this point? Now, I need to find formulas for an and bn in terms of the initial data. So I need to enforce the initial conditions, both of them, on this solution formula. So for example, suppose I go through here and set t equal to 0. Well, what will happen in this case is here I'll have sine n pi x over L plus sine n pi x over L. So those just add together and divide by 2. So I'll have an times sine n pi x over L. Over here, if I set t equals 0, these cosines are equal, so they'll cancel out. So the bn part goes away entirely. So now I have this equation. So u of x0 is supposed to be f of x by initial condition. So the an's are the coefficients of a Fourier sine series of f of x, like we've seen before. Similarly, suppose I take the derivative of all this with respect to t, and then set t equals 0. So that's my other initial condition. Ut of x0 must be equal to g. So what ends up happening is, if I take a derivative of this part with respect to t, I'm going to get the cosine of all this times the derivative of this with respect to t, which is going to be n pi c over L. And here I'll have minus n pi c over L. In other words, these will cancel when I take a derivative with respect to t and set t equals 0. Whereas these terms, the cosines, you differentiate them and you'll get sines. And the terms will add together rather than canceling. So I won't go through all the algebra on that, but you take that whole derivative with respect to time at t equals 0, and you set that equal to g of x, because that's your other initial condition. And once again, we have a Fourier sine series, except you have these extra scaling factors. So you have c times n pi over L. So the way that you would handle that is you would go ahead and compute the Fourier sine coefficients of g of x like you did for f of x. But instead of simply saying, oh, that's bn, you have to divide by c and divide by n pi over L to get the correct coefficients. And actually, I'm going to fill in the formulas for that right here. Okay. Actually, probably need this line right here, but I'll leave it in there. So to give you a formula for your coefficients, so an is going to be 2 over L where'd it go? Oh. Times the integral of 0 to L of f of x sine n pi x over L x. All right, so you've seen this before from the Fourier sine series. And then similar for the bn's, where you have g of x, but as I mentioned earlier, you have this scaling factor to consider that I have to multiply by L over Cn pi. Okay. All right. So actually, what ends up happening is that the L's will end up canceling because of that. But I wanted to write it like this so you can see where this coefficient L over Cn pi comes from. It's a reciprocal of the scaling factor Bn that you have in here. So you just have to remember to compute Fourier sine coefficients, so basically it's a finite sine transform. You just have to scale by L over Cn pi, and you're done. What I'll do here is write this a little differently. Put it up front. That way it's separated. coefficients of f and of g, this one you scale. Alright. So that's what you do with solving a problem by separation of variables. Solving this kind of PDE by separation of variables. That here's how you get your coefficients. So now what I'll do is, I want to show you where this comes from. I don't have it written out here, so I'll fill that in now. Alright, so go back up here and fetch the previous formula. Okay, so what I need to show you is how do we get from here to this result here that you recognize as the Algebra solution from the Cauchy problem. Okay. All right. So first I'm going to break this up into multiple summations. So first for the AN terms. So let me use brackets more. Oh, something went wrong there. That's weird. Okay. And then I still have a factor of 1/2 throughout. All right, so now I've broken these sums up. And then here, I have a difference of function values. The same, so like the situation like f of b minus f of a can be written as the integral from a to b of a derivative of this function. So that's what I'll do here. I'll write this as an integral from x minus ct, x plus ct. Not sure why all that went away. Oh, it's a avoided bracket. Okay. All right. And then I'm taking the derivative of what's in here. So my integrand, okay, so I'll get rid of this. All right. So my integrand would be, I'm going to use a different letter inside. So it's cosine of n pi s, n pi s over L, except it's not cosine of n pi s over L, it's the derivative of this function. Well, the derivative of that would be cosine would be minus sine of this. And then I have to multiply by the coefficient of s, which is n pi over L. So I'll pull that constant out. Okay. All right. But this minus and this minus will make a plus. So go ahead and fix that. Oh, and because I've broken up into separate sums, I need 1/2 times the summation in front of that too. Okay. And actually what I'm going to do is, I'm going to move the summation and the Bn n pi over L inside the integral. I'll leave the 1/2 out of it. Okay. So, so now we have a Fourier sine series inside the integral. Okay. So now we need to make sense of all this, because if we look up here at our equation for G is equal to Bn n pi over L times C times sine n pi x over L. Here I have this factor of C, which I do not have in here. So I'm going to put it there. I'll put a C here, and then I'll put a C out here. So now we take a look at everything that is inside the summation. So inside the integral rather. So C sum of Bn n pi over L sine, and I compare that to this. It's G. It's exactly G. So this right here, this is a Fourier sine series for f, except instead of x, you have x plus ct. This, I need my an here too. Also, Fourier sine series for f, except instead of x, it's x minus ct. So this part is 1/2 f of x plus ct. This part is 1/2 f of x minus ct. And then since all of this is equal to g of s from what's above, I have 1/2c integral from x minus ct to x plus ct of g. So the Dilembert solution formula in this case, again, falls out. The questions about what happened here.
Is there supposed to be a c in front of the summation for 1/2c? The Bn part.
Up here?
Yeah.
Well, yeah, that is supposed to be there because what I had earlier, I had this 1/2 and there were no c's, but I wanted to get what's inside here to match with this. So I could replace with G. But I didn't have a C before. So I put it there, but then I had to divide by it.
Okay.
And sure enough, that matches 1 or 2 C's in the answer. Other questions? I know all of you else had a test, so look at the schedule. Okay. Okay. Yeah, so what I just covered today, beyond the next homework, that's due 1 week from today. And I know there are some homework assignments outstanding. There's a few, but I still need to grade. I'll get to that within a few days. So already questions from prior homeworks. Okay, I guess we're calling it good.